Assalamu alaikum everyone. We have 5 members today: Arkam, Ahmed, Asad, me and Bakar. And Arkam will explain about solid state physics, and Asad will explain about quantum doors. Ahmed will explain about applications of quantum doors, and I'm going to explain you Bloch theorem, and further Bakar will explain to you Kronig-penny model. So let's start.
Thank you so much, Talha. So class, today I'm gonna present you what are solid state physics. It is a branch of physics that deals with the study of rigid matters. It is also done through the variety of methods including quantum mechanics. For example, rigid matters, solids, electromagnetisms, metallurgy, etc. Now move on the basic function of these devices. The basic function of solid state physics is to how the atomic properties of a solid material affect its overall properties. It did not emerge as a separate field of study till the 1940s, although the properties of solids have been studied by scientists for centuries. But what they are made up of? Every solid material is made up of densely packed atoms. The mechanical, electrical, optical, thermal, and magnetic properties of atom are all dependent on the interaction of the atoms making it up. The alignment of atoms in a regular geometric patterns or an irregular pattern depends on the material and involved and the conditions under which it formed. Main examples are crystalline solids such as metals, amorphous solids. But the question is, what is solid state devices? The solid state devices that contains components that do not depend on electronic conduction in a vacuum or a gas. They are solid state devices. Semiconductors like resistors, capacitors perform the electronic function of a solid state devices. In simple words, we can say the electronic device in which electricity flows through solid semiconductor crystals. You can take some examples like silicon, germanium, gallium. Now comes the history of such devices. Transistor is considered to be the first widely used solid-state device and is still used in almost all electronic devices today. It was developed at the Bell Laboratories on December 23, 1947. It is a component used to control the amount of current or a voltage of an electronic signal. The picture shows several examples of transistors. The transistor is a primary building block of all microchips, including your CPU. It is what creates binary zeros and ones bits your computer uses to communicate and deal with Boolean logic. My friend, the question is, what technology might succeed transistors? Transistors are still used in all electronic and likely to be used for the future. However, there are some promising technologies such as carbon nanotubes being developed by IBM. Now come to the semiconductors. Materials that have the resistance levels between those of a conductor and an insulator are referred to as semiconductors. They are quite common, found in almost all electronic devices. Good examples of semiconductors are germanium, selenium, and silicon. But silicon is used in most semiconductors for computers and electronic components, as it is considered to be the best semiconductor materials. A semiconductor's quality is measured as a value of electrical conductivity, which is how well a material conducts electricity. As the temperature rises in a semiconductor, its conductivity increases due to decrease in resistance in the material. Many companies manufacture semiconductors, including Intel, Samsung Electronics, Texas Instruments, and Toshiba. They are components and devices that uses semiconductors such integrated circuits, keyboards and mouse, monitors, processors, transistors. Application of solid state physics. Solid state physics is applied rapidly all around us. The most important among them are electronic devices such as mobiles and computers, optical devices such as laser and fiber optics, magnet-based devices such as magnetic resonance imaging, and vibrating devices, silicon-based logic and memory bits. In other words, the whole concept of modern technology is based upon the principle of solid state physics. Even regular things such as the writing in a building, the window pane, the magnet in the refrigerator door are all dependent on the principle derived from solid state physics. What are the applications of transistor in daily life? The transistor is a semiconductor device and is used to regulate the supply current or voltage. It can be used as a switch in electrical circuits and also used as an amplifier. So here we sort out the main application of transistor for you. Here we list the application of transistors. Applications are used in digital and analog circuit as a switch, used in signal amplifier devices. Cellular phones would be one of the most widely used applications of transistors. Every cell phone uses a transistor amplifier. Number 4, uses in power regulator and controllers. It is used in modern electronics. IC uses in almost every electronics applications. Transistors are used in building some of the integrated circuits. The microprocessors includes more than billions of transistors in each chip. Transistors are used in almost every electronic devices, from stoves to computer and from pace markets to aircrafts. It is used in calculators, computer, radios, and also hearing phones, every daily life devices which requires good sound quality. Because transistors are often used in amplifying circuits. The military use transistors, high power radio frequency abilities in radar. The summary of these applications are that transistors are a basic semiconductor device which uses for regulating the current and voltage in small electronic circuits. Transistors are used in many amplifying circuits for amplifying weak signal. Nowadays they are used in almost very electronic devices. Cell phones contains a transistor circuits as a sound amplification circuit. Transistors are so small in size so that the size of modern IC reduced and we got benefited. They are used in some aerospace applications also. So by the one line we can say, because of invention of transistors, modern electronics is possible. Hopefully you understand the application of transistors in our daily life. Now Asad will tell you about quantum dots.
चलो स्टार्ट करो. Thank you, Arkham, for giving a cogent introduction to solid-state device that must have showed how handy tool it can be on our daily life. Now I am going to discuss another interesting applications of solid-state device like quantum dots. What are quantum dots? Quantum dots are small semiconductor particles with typical sizes that range from 1 nanometer to 10 nanometer. They are zero-dimensional nanostructure. They are artificial clusters of semiconductor atoms that have the ability to confine the electron's motion due to their small size. They can produce distinctive colors determined by the size of the particles. Quantum dots are microscopic. The size of quantum dots relative to a human is like the size of a human relative to the sun. Quantum dots are tiny crystals. In other words, we can say as nanocrystal of semiconductor materials. They display unique electronic properties intermediate between the bulk semiconductors and discrete molecules. I need to mention it's because of the unusually high surface to volume ratio of these particles and confinement due to the limited number of atoms and special shape of quantum dots. Well, I need to tell you little bit about the energy levels first. So let's start energy levels. To understand the mechanism behind the quantum dots, we have to recall first that electron emits in the direct energy level in the bulk semiconductor. So in solid, when we have a billions of atoms and these orbitals makes connection, the concept of bonding, and by that a single level of energy, and we get a load region of energies which is called energy band. In case of metals, these bands are continuous, but in insulator there is a remarkable band between the energy band, and in semiconductors stay in between them, and but have a band but not as long as insulator, but there is a still band, like you can see in the figure. The bulk semiconductor structure, two important bands are valence band and conduction band. Valence band is the lowest energy level and that electrons have occupied, but in case of conduction band is the highest energy level and high energy band that is empty, and there is a gap between them which is called energy band, or band gap. Band gap is a very critical parameter in many electronic and optical applications, and there are tons of research to tune band gap value. If light is emitted to semiconductor, some electron acquire enough energy to jump from valence band to conduction band, and since higher energy levels is not variable, and after a while they may want to come back to the valence band and release different energies between the valence band and conduction band. Actually they release photons with the specific wavelength of light. So why does this matter for us? Because in quantum mechanics energy relates a wavelength. As a matter of fact, that difference of colors that we see there are different packets of photons or different wavelengths. But what happens with quantum dots? In quantum dots have different size and shape and made a limited number of atoms, as we have discussed earlier, and we have sets energy individually energy levels. These sets of energy are close together, but still we have a band gap between these sets of energies. Interestingly, it depends on the size or the number of atoms and band gap charge. We will know later on different size of quantum dots. In this slide, we will discuss the size of quantum dots. As you know, we have discussed earlier in previous slides, quantum dots are nanoscale man-made crystals that have the ability to convert the spectrum of light into different colors. Each quantum dot emits a different color depending on its size. So here we have different size of quantum dots, like 2 nanometer, 2.5 nanometer, 3 nanometer, 5 nanometer, and so on. So if we follow a specific wavelength of light, like you can see in this figure, blue light, which is wavelength for 15 nanometer, if we fall on these quantum size, they produce different colors. So here we can say a smaller quantum dot, which is 2 nanometer in size, it emitted light green light, and 2.5 nanometer emitted green light, and 3 nanometer emitted light green light, and 5 nanometer emitted golden light, and 6 nanometer of quantum dot size emitted red light. So they are made up of same material. So I want to mention here, smaller quantum dot size get larger the band gap and more energy is released. It means it has high energy and high frequency, and at the end we get more bluish color. In case of larger quantum dot size, we get smaller band gap, and we get low energy. It means it has low energy and low frequency, and we get more reddish color, as you can see in this figure. Like if we have discussed 6 nanometer in size of quantum dots, it emitted red color. So here we have conclude the size that colors produce in distinctive colors, like blue, red, green, gray. So it all about, it's depend on the size of the quantum dots. Now my friend Ahmed is going to tell you about how useful quantum dots can be in a whole variety of application.
Wide range of useful. Thank you so much, Rahan Saab. No doubt quantum dots is very exciting discovery and used in a wide range of application. Now I'm gonna tell you some of useful application of quantum dots. First application of quantum dot is computing. Quantum dots technology is one of the most promising candidates for use in solid state quantum computation. By applying small voltages to the light, the flow of electrons through the quantum dots can be controlled, and thereby precise measurement of the spin and other properties therein can be made. With several entangled quantum dots or qubits, plus a way of performing operation quantum calculation, and the computer that would perform them might be possible. Now another application of quantum dot is QLED. Quantum dots may someday light your homes, offices, streets, and entire cities. Quantum dots LEDs can now produce any color of light, including white, orange, yellow, etc. Quantum dots LED are extremely energy efficient. They use only a few watts, while a regular incandescent lamp uses 30 or more watts for the same amount of light. Another application of quantum dots is photovoltaic device. Quantum dots may be able to increase the efficiency and reduce the cost of today's typical silicon photovoltaic cell. Quantum dots photovoltaic would theoretically be cheaper and manufactured, as they can be made using simple chemical reaction. Now move forward to the cell imaging. Quantum dots last longer in your system and are brighter than many organic dyes and fluorescent protein previously used to illuminate the interior of the cell. They also the advantage of monitoring changes in cellular process, while the most higher resolution technique like only provide image of cellular process frozen at one moment. Quantum dots, red dots above, can be designed to bind the specific cell receptors. Green thing. In this way, researchers can monitor all kind of process in living cells. Thank you so much.
Bloch theorem is a very fundamental theorem of quantum mechanics, and it is used to solve crystal array of structures. And it's all about symmetry. And you are very familiar that symmetry can make our life very simple. And now we imagine that there are some dots and a man standing on the dots. As he moves towards the right or to left, he'll see the same pattern. If he moves towards A is the spacing between two dots. If he moves A towards right or towards the left, he will see the same pattern. And same is the case with wave function. We do not take wave function because there is no physical interpretation of wave function. Rather than we can take a square of wave function and we call it probability. So the square of wave function at x will be equal to the mod of the square function of x plus a square. That shows that the probability of finding electron in any part of the crystal array is the same, and this is the one condition. And the other condition is if we go towards the end, we will get the same function as it is before. So we can imagine that it is just a circular lattice that is repeating itself. So the psi at x will be at psi plus a, psi plus 2a, psi plus 3a, and so on. So it is just repeating itself. So we get two boundary conditions. One is psi of x square, that one is equal to psi of x plus a square, and other is psi of x plus a, and other is psi of x plus a is equal to c times of psi plus x square. The first boundary condition is rather probability, and the next boundary condition is related to the nth term of these psi squares. Now if we see the pattern, psi plus a is equal to c times psi of x, and psi of x plus 2a is equal to c square times x plus a. In the possible pattern, we can see the psi of x plus na. Then we have moved to the nth number of the right or left, where n indicates the number of iteration that we have moved. So we will get cn psi of x, just the geometrical pattern that we can see. Now we know that psi of x is multiplied by some factor in the given psi of x. The factor is c raised to power n. So we can imply that c power n equal to 1. And if c raised to power n equal to 1, then c is definitely equal to the nth root of 1. And in mathematics, if we solve for nth root, we get e raised to power iota 2 pi s by n x plus a. And if we are dividing it by a just to make the quantity dimensionally consistent, So psi of x is equal to iota 2 pi s over n x over a. And we can take this factor out. 2 power s over n, we called it k. And then our equation will become e to the power I kx. Well, this is not the only thing that can be constant, that can show periodicity, and that can be repeat itself. There are other functions as well. We call them global functions. That is uk of x. And it can be anything. So the Bloch theorem say that psi of x can be written as e to the power I kx ukx. And it is very useful function in quantum mechanics. And later we will see on how can it apply on Kronig-penny model. We can use it to solve the problem of electrons moving in one-dimensional lattice, and we can find the solution of it. Thank you so much for listening me till the end. Now Abu Bakr will explain the Kronig-penny model and the application of Bloch theorem. Thank you.
Once Talha has talked about Bloch theorem, I am going to talk about Kronig-penny model. Kronig-penny model is a very handy tool in quantum mechanics used to solve the problem of electron moving in one-dimensional crystal lattice. In that, we assume that the potential of electron varies periodically as it moves between the one-dimensional structure. We take the potential energy of electron to be zero when it is very close to the nucleus, and maximum V is equal to V naught when it is between the two adjacent nuclei and the interatomic spacing is A. So here is a pictorial representation of how we would expect the potential to vary with displacement. Here we can define two regions. One is the region 1 where potential is 0, that is when the electron is adjacent to the nuclei, very close to the nuclei, and region 2 when it is between the two nuclei, between the two adjacent nuclei. So in case 1 the potential is 0, and in case 2 the potential is maximum, that is V naught. In quantum mechanics, whenever we encounter any problem, the first thing we have to do is to solve Schrödinger time independent equation, and that's what we are going to do. We apply Schrödinger equation for the both cases, and we get two equations, equation 1 and equation 2. In equation 1 and 2 we see a factor 2m over hk square e psi, and in equation 2 we see a factor 2m over hk square e minus v naught psi. In this 2m, the term that is on the left side of the psi is constant, so we assign them the values of alpha square in case of equation 1 and beta square in case of equation 2. Now what we do is we substitute the value of alpha square and beta square in equation 1. Now once we substitute the value of alpha square and beta square, we get the equation 4 and 5. The next step is interesting. We know that the potential is varying periodically, so we use Bloch theorem. And in Bloch theorem we take psi is equal to e to the power I kx ukx, since it is varying periodically, and e to the power I kx is used for periodic functions. Now we have taken psi as e to the power I kx ukx. We have to take the second derivative of psi, which is done in equation 7. Once we have found the second derivative of psi, what we have to do is we have to substitute d to psi by dx square in equation 4 and 5 to get equation 8 and 9. In equation 8 and 9, what we have done is we have simply substituted equation 7, that is second derivative, into equation 4 and 5. We get these two equations. We can solve these two equations and get the general solution. We get two solutions, u1 and u2. Now what we can do is that we can solve these two equations to get another equation, and that is the most fundamental equation of Kronig-penny model, that is p over alpha a sine alpha a plus cos alpha a is equal to cos ka, where p is the potential, alpha a is the interatomic distance, alpha is some constant, and k is the wave number. K is equal to 2 pi over lambda. So now we solve that equation for two cases. In first case, when potential is infinite. When we solve for potential is equal to infinite, in the equation we can see that the second term and the third term on the right hand side of the equation, they will just vanish away, because once we divide something by a very large number, it gets to 0. So what we will be left with is sine alpha a is equal to 0. Now in quantum mechanics 1 course, we have seen when we solve the situation like this, sine alpha a is equal to 0, we get the values of equal to n pi. It is exactly the same that we did in quantum mechanics 1. From this we can find the values of energy using very simple mathematical substitution. There is nothing complex in it. We get the energy as n square, where n is the order of energy. N can be 1, 2, 3, 4 up to infinite. H square, with H is Planck constant, and 8 ma square. M is the mass of electron and A is the interatomic distance. Now the interesting thing is that what we have found out for energy of that electron is exactly the same thing that we have found out in quantum mechanics for particle in a box. It's just like particle in a box, and it is the case of an insulator. So when an electron moves as an insulator, it's just like it's moving in a particle trapped in a one-dimensional box. Next we tread towards the case 2. In case 2 we put potential is equal to 0, and after doing very simple mathematics we find the energy of electron is equal to p square over 2m, which is just kinetic energy of the electron. Now if we think deeply over it, it's exactly the same thing that we get in quantum mechanics for solving for particle, for a free particle. That's exactly the same thing. So Kronig-penny model is a very handy tool. We can find out the nature of conductor as well as nature of insulator. In case of conductor, it's just the electron is just moving like a free particle, and in case of insulator, it's just moving like it's trapped in a one-dimensional box.